So what is this total solar irradiance? Okay, so what this map is giving you is the total solar flux in watt per meter square, total horizontal solar flux in watt per meter square integrated over the entire day. Okay, so this is the daily total. So a flux is watt per meter square. What is joules per second per meter square? Now you integrate over the total number of seconds over the day, and this becomes the total energy that is incident on the horizontal surface as a given point in the world over an entire day. Similarly, you can integrate over the entire year, and that becomes the yearly total. And the units here are being used as kilowatt hour per meter square. Okay. So this kind of gives you the total energy that is available on a daily basis or on a yearly basis on average at different parts of the world from the sun. Okay. And what you can see is the values are changing from around 7 to around 2. So a large difference depending on which part of the world you are in. For the daily totals and the yearly totals is 2700 kilowatt hour to 800 kilowatt hour. Now there is something that you should note. What this figure shows that even at the higher range, the solar energy is relatively dilute. So you are thinking of say a 100 megawatt power plant, right? So 100 megawatt power plant will generate 100 megawatt hour of electrical energy on an hourly basis, correct? So that you multiply by 24 and you get 2.4 gigawatt hour of electricity generated per day. Okay. Here, however, on a square meter of land, you are generating only 7.4 kilowatt hour of energy is available. Forget the conversion efficiency. Even if 100% conversion happens, 1 meter square of area will generate maximum 7 kilowatt hour of energy, even in the best places of the world. So then 7 kilowatt hours, if you want to move it into a gigawatt hour range, like 7 gigawatt hour, you need a 1000 meter square of area. Okay, so at least 1000 meter square means like 100 meters cross 10, 100 meter cross 10 meter area. So even forgetting the efficiencies, if you put the efficiency values which is around 20%, 25%, you will have to increase this further. So you need reasonably large tracts of the ground to generate energy at the same kind of values as we would do for a power plant or a hydel power plant system. Okay, so that part you need to remember. Okay. However, the land area footprints are reasonable, and in many places, because solar energy is widely available, you do not have to put those on lands that are being used for other purposes like housing or agriculture. You can put it in lands that are not being used for commercial or residential activities. So that advantage is there for solar power. Now, if you look at the distribution of solar energy, you will see that most of the solar energy is concentrated in the equatorial and subtropical zones of the world. So you can see this is the equatorial zone. The two subtropical zones, the northern subtropical zone here and the southern subtropical zone here, are showing the largest values of daily or yearly solar energy, horizontal solar energy irradiation. And the reason is these regions are relatively dry and arid, so have low cloud cover. So clouds of course reflect a lot of the sunlight back. So you should not have clouds if you want to have good sunlight. So these regions, Sahara, Arabia, Western India, Central Australia, Southern Africa, regions of Southern Brazil, etc., and Texas, Eastern Mexico, these are dry, arid regions with low cloud cover, and because they are close to the tropics, they have very high incident solar radiation values. So those two together makes it so that these regions are especially good for solar energy flux, high solar energy flux. India, because they have reasonably large cloud cover, is in the moderate zone, but still very reasonably good solar energy values are available in India as well. Okay, Tibetan Plateau, because which is high and dry, even though it's cold, it receives a lot of solar insolation. So that is also another good place where you get a lot of solar energy. Okay. But if you go to higher latitudes, the temperate zones and the Arctic zones, you see because of the high latitude, the solar energy flux also attenuates. You are getting less solar insolation per meter square of horizontal surface area, and also because of the larger cloud cover there, the solar energy flux decreases further. Okay, so these two effects means that high latitudes temperate regions are not that great in generating good amount of solar electricity. So as a rule of thumb, the subtropical countries are the best places to situate solar power plants, whereas temperate countries are not as good compared to them in terms of generating solar energy from solar cells or solar thermal systems. Note, this is exactly the opposite of the wind energy. So wind energy is more, the availability of wind energy is greater in the temperate and high latitude regions, and it's lesser in the subtropical and the tropical belt, whereas for solar it's the reverse. Tropical and subtropical belts have the highest solar insolations, and the solar insolation progressively drops at the higher latitudes. So if you think of the kind of renewable energy mix you would want for a country, if you are in a low latitude country, you would go for more solar and less wind, whereas if you go for a high latitude country, you may go for more wind and less solar. So that kind of a design consideration becomes evident when we look at these two maps in comparison. This is the values that are available for India, global horizontal irradiation, daily totals and yearly totals. As you would expect, the arid regions in Western India are some of the best places for having solar cells, as well as the low latitude regions in Tamil Nadu, Telangana. These are high plateaus, and so these have relatively higher solar insolation, also because these are at lower latitudes. Overall, once again, because of clouds and fog cover, the North Indian plains are not as well endowed, but still the values are high enough for good quality commercial solar cells to operate. Remember, there are significant solar power plants, solar cell based photovoltaic solar cell farms in Germany, in UK, which have very low solar irradiation. So overall, India throughout is well endowed, but particularly the Western India and Southern India is well endowed compared to other places in India. This gives you the daily solar insolation with latitude and with seasons. So solar insolation, the proper term for the integrated flux is insolation. Okay, irradiation is the flux in watt per meter square. Insolation is kilowatt hour per meter square per day. So the unit is energy instead of power. So then it's called solar insolation. So solar insolation is the measure of the amount of solar energy received on a given surface area in a given time. It is the integration of solar irradiance over time. Its units are either kilojoules or kilowatt hour per meter square per day or per year. Okay. And this is the graph of solar insolation with latitude and with the season of the year. Okay, so if you see the equatorial zone, the average solar insolation on a clear day, so the cloud cover part has been removed from the expression, is around 25 to 28 and remains reasonably constant. Okay, if you are looking at 12 degree north or 12 degree south, you can see in the 12 degree north primarily. So 12 degree north and so this is basically the winter season in the northern hemisphere and the summer season in the southern hemisphere. So the way these months are given, in the northern hemisphere this is July, August, September, October, November, December, January, February, March, April, May, June. In the southern hemisphere the months have been shifted by 6, so this becomes January, February, March, April, May, June, July, August, September, October, November, December. Okay. The advantage is the winter season in the northern hemisphere is December, January, February. In the southern hemisphere it's June, July, August. So the winter season is highlighted here together. The summer season is July, August, September, June, July, August, September in the northern hemisphere, and December, January, February, March in the southern hemisphere. So again, the summer season is clumped in the same point. Okay. So in general, in the winter season, you are getting low solar insolation everywhere, but the effect is far more pronounced as you go higher up in latitudes. So in the winter hemisphere at 36 degree north or south, the insolation is around 30 megajoules per meter square per day, whereas in the summer that goes up to 30 megajoules per meter square per day. So there is a sharp dip of solar insolation in the winter season, especially in the at higher latitudes, and this causes an overall decrease in the annual solar insolation that is received by a location as you go higher up in the latitude. So for example, if you look at 60 degrees, the values are below 5 megajoules per meter square per day between October to February in the northern hemisphere. Okay. So this cannot be compensated by the still reasonably high insolation values in the summer hemisphere in the summer season in that same latitude. So that is why you are getting lower and lower values of yearly or daily average insolation in the high latitudes. Okay. So the next part of our lecture that we will start today and will continue in our next lecture is how to evaluate these values. How to evaluate what is your hourly insolation values in the winter compared to summer. How to evaluate how many hours of daylight you are getting, because that is also changing from season to season, correct? So those things are very important in order to properly understand how much solar energy you are actually getting at a certain location. So we will look at those aspects now. In order to study those aspects, we have to define certain things. The first thing that we define is what is called the solar declination angle. So the solar declination angle is the angle between the position of the sun at noon on a given day and the position of the sun at noon on the date of the equinoxes. Okay. So remember, the equinoxes fall on March and in October, the spring equinox and the autumn equinox. And on those days, you get equal number of daylight hours and night hours throughout the globe. So at equinoxes, you have the northern hemisphere and southern hemisphere are exactly are not inclined with respect to each other, far away or away from the sun. So these are the equinox positions. So for both cases, you are getting 12 hours of daylight and 12 hours of night throughout the globe, from the North Pole to the South Pole. So there is no inclination of the axis of the earth with respect to the sun. Whereas in the summer times, the northern hemisphere is inclined towards the sun and the southern hemisphere is inclined away from the sun. And in the winter time, the northern hemisphere is inclined away from the sun and the southern hemisphere is inclined towards the sun. So in summer, you get northern hemisphere gets more than 12 hours of daylight. Southern hemisphere gets less than 12 hours of daylight. Whereas in winter, opposite is the case. Northern hemisphere gets less than 12 hours of daylight. So here I am, by winter, I am meaning November, December, January, February, those months. Okay. With northern hemisphere winter and it's the southern hemisphere summer at those times. So northern hemisphere is getting less than 12 hours of daylight and southern hemisphere is getting more than 12 hours of daylight. And you will see that the sun at noon, the angle that the sun makes with the local normal to the horizontal land is changing with the seasons. Okay. So the declination is basically a measure of the relative migration of the sun's noontime angle with the seasons. So first we measure what is the angle that the sun is making with the ground at the equinox days. There will be a certain constant value. Then the angle that the sun makes at noontime at any other day with that angle during the equinox day is the declination of the sun. Okay. And this declination is basically shifting in accordance to the axial tilt of Earth. So it goes from plus 23.44 to minus 23.44. Okay, so this is shown here. So this is the angle that the sun makes with the ground normal at equinoxes, and this is the angle that it makes in the summer solstice, and this is the angle it makes with the winter solstice. So this is plus 23.44 and this is minus 23.44. Okay, so that's how the differences are. So the angle between the position of the sun at noon on a given day and the position of the sun at noon on the day of the equinoxes, this value is the declination. And we can evaluate the declination angle on a given day using this formula, where declination angle delta on a given day is given by delta naught, which is 23.44. Delta naught is plus 23.44 in summer solstice, minus 23.44 in the winter solstice, into sine 360 degrees into 284 plus n by 365. Okay, so we kept delta 0 is 23.44. N is the day of the year. So January 1 is the first day, January 2 is the second day, December 31st is the 365th day of the year. So this N is the day count. Okay, so if you use this formula, delta 0 sine 360 degrees into 284 plus n by 365, this angle will be in degrees. Okay, then you will get the declination angle for that given day, the nth day of the year. So this is how we can find the position of the sun relative to its position in the equinox at noontime. So that's number one. Another thing we need to know is the latitude angle phi. So you know equator is 0 degrees, right? Tropic of Cancer is 23.5 degrees. The Arctic Circle is 60 degrees. Okay, 66 degrees. So these are the latitude angles. It is the angle that a given point on Earth's surface makes with the equatorial plane. Okay, so a point on the equator obviously lies on the equatorial plane, so its angle is 0. Any point on the northern hemisphere will vary from 0 to 90 degrees, with the north pole being making an angle of 90 degrees with the equatorial plane. Whereas if you go in the southern hemisphere, it will be 0 to minus 90 degrees. So the what we call 30 degrees south is basically minus 30 degrees. 40 degrees south is minus 40 degrees. So the equatorial angle, the latitude angle of the southern hemisphere is negative, 0 to minus 90. That for the northern hemisphere is 0 to plus 90. So that is the latitude angle of a given location. So you know given the time of year, you know the declination angle, and you know given the position, you know the latitude of that point, and you know the latitude angle. Given these two values, you can actually calculate the number of daylight hours that location will have on that given day. So you know the nth day, so you know the declination. You evaluate tan of the declination angle, tan delta. You know the latitude angle, psi, plus 90 degree to minus 90 degrees, whatever, and this you get tan psi. Okay, so tan psi into tan delta, this value minus of that and cos inverse. Now this value, finally, the cos inverse of this value will be given in degrees. You multiply it by 2 by 15 and get the number of daylight hours in hours. Okay. For example, if the latitude angle is 10 degrees, this is tan of 10 degrees. Declination angle says minus 10 degrees. Then tan of minus 10 degrees. You get a value. You put cos inverse of minus of this value. And you get an angle in degrees. Multiply by 2 by 15 to get the number of daylight hours for that position on that given day. Okay. Note that if minus tan psi tan delta is greater than 1, so cos inverse can only go from 1 to 0. Okay. So this value, I will just check this. This is mistaken. So the idea here is, I will just explain this clearly. In some cases, so the cos of an angle can be will vary from plus 1 to minus 1. Okay, if it's greater than plus 1 or less than minus 1, then you have either 0 hours of daylight or 24 hours of daylight. Okay, so this will be less than -1 and this is greater than +1. Okay, then this becomes non-physical, right? So if you get minus tan xi tan delta to be greater than +1, then you have 0 daylight hours. Okay, and if it becomes this minus tan xi tan delta becomes less than -1, then you have 24 hours of daylight. Okay, so that way you can find the number of daylight hours in this location. Okay. And theta is the angle between the normal to the solar collector surface and the sun. So this, you know the number of daylight hours now. Now suppose you have a collector which makes which is given at an angle with respect to the ground. Many of the solar cells you will see is put at an incline with respect to the ground. Okay, so the angle that the solar collector makes with the ground, we call it beta. Okay, and the angle that the normal to the solar collector makes with the sun is the angle theta. Okay, this is different from theta z, which is the angle that the ground normal makes with respect to sun, and this is the angle that the collector normal makes with respect to the sun. Is theta and theta z. So in the next class we will discuss, given all of this that we have evaluated, how to find what is the actual incident flux on an inclined solar collector. So stay tuned for the next class's lecture. Thank you.